In the deepest layers of matter, a photon decides what it is only when you look at it. Particles whisper across galaxies in an instant. A cluster of 7,000 atoms exists in two places at once. We thought reality had rules. We were wrong. You're about to see a metal grain that behaves like a ghost, a cat alive and dead for 23 minutes, and a connection between particles that should be impossible. If this fascinates you, hit subscribe so we can keep exploring together. Prepare yourself. We begin. Imagine flipping a coin, and before it hits the table, it is neither heads nor tails. It is both. It is everything it could be at once. This is what particles do every moment of every day, and the science behind it is real. In our world, things are either here or there. A car is parked or driving. A door is open or closed. But shrink down small enough, smaller than an atom, and the rules break. A single electron does not sit in one place. It exists as a smear of possibilities, spread across many locations at once. Scientists call this superposition. For a long time, people argued that this only happened to tiny things you could never see. Then, in early 2026, physicists in Vienna did something almost unthinkable. They took clusters of about 7,000 atoms of sodium metal, fired them at a narrow slit, and watched them spread out like a wave. Each cluster existed in multiple positions at the same time, separated by a distance more than 15 times their own width. Think of it like a single grain of sand passing through a window and somehow ending up on both sides of the wall. That is what happened. And it was filmed by detectors. It was measured. It was real. The team that did this beat the previous record for macroscopicity by a factor of 10. That word, macroscopicity, is a fancy way of saying how big and clunky an object can get while still acting like a ghost. The bigger the object, the harder it should be. Yet here it was, working with thousands of atoms bundled together. Picture a swarm of bees flying through a doorway. In our world, every bee picks one side. In the quantum world, every bee somehow takes both sides, and the swarm interferes with itself like ripples on a pond crashing into other ripples. That interference pattern is the signature. That is the proof. But here is the strangest part. The moment you try to peek and see which path the cluster actually took, the magic dies. The wave collapses. The cluster becomes a single point, like any normal object. Reality only shows its weirdness when nobody's watching. Scientists have a name for that final snap from many possibilities into one outcome. They call it the measurement problem. And nobody, after 100 years of arguing, agrees on what causes it. Is it the observer? Is it the detector? Is it the universe itself making a choice? Some say the cluster always had a definite position, and we just did not know it. Others say the universe splits into copies, one for each possibility. Still, others say consciousness itself collapses the wave. All three ideas are still alive. None have been killed. What you should take from this is simple. The solid world you see, the table, the chair, the floor under your feet, is made of particles that, when nobody is looking, exist as clouds of pure possibility. The world becomes solid only when measured, which raises a chilling thought. If the act of looking changes things this much, then what was the universe doing before anyone could look at all? Stranger discoveries are waiting in the next chapter, where a single particle takes two paths at once and somehow knows. A single photon flies toward a wall with two narrow slits cut into it. Behind the wall sits a screen. Logic says the photon must pass through one slit or the other. Logic, in the quantum world, is wrong. This experiment is called the double slit experiment, and it is the most famous puzzle in all of physics. When you fire photons one at a time through those two slits, with nobody watching which slit they used, something impossible happens. Each photon lands on the screen as a single dot. So far, normal. But after thousands of photons, the dots form stripes of bright and dark bands. A pattern only waves can make. Each single particle somehow interfered with itself, as if it had passed through both slits and met on the other side. In late 2025, a team at the Massachusetts Institute of Technology stripped this experiment down to its purest form. They used single atoms as the slits and single photons as the test subjects. Even with all the clutter removed, the result held. Light exists as both a particle and a wave, and this duality cannot be observed at the same time. The MIT team also showed Albert Einstein was wrong about one of his arguments against this strangeness. Picture a person walking up to a Y-shaped fork in a road. In your world, the person picks left or right. In the photons world, the person walks down both roads at once, meets themselves at the end, and either gives themselves a high five or a punch in the face, depending on the angle. That high five or punch is the interference pattern. Now, here comes the part that breaks brains. Put a tiny detector at one of the slits, just to peek and see which one the photon used. The moment you turn that detector on, the stripes disappear. The screen shows two simple blobs, exactly what you would expect from particles flying through holes. The pattern dies. The wave behavior vanishes. The photon seems to know it is being watched. There is no force pushing on it, no physical interference. Just information. Just the simple fact that somewhere, somehow, a measurement was recorded. That is enough to change what the photon does. Imagine you are walking through a hallway, and the second you realize someone is filming you, you suddenly stop bouncing off both walls and walk straight down the middle. That is the photon. Awareness, in some strange sense, matters. What constitutes a measurement, though? Does the detector itself collapse the wave, or does a human eye need to read the result? Scientists still argue about this. Some think any interaction with the environment is enough. Others think information must reach a conscious mind. The honest answer is that nobody knows for sure. This experiment has been repeated thousands of times, with photons, with electrons, with whole atoms, even with molecules made of hundreds of atoms. Every single time, the same result. Watch, and reality behaves. Look away, and it goes wild. The universe seems to care whether it has been seen. Which leads to a question that haunts physicists to this day. What is so special about looking? And as you're about to see in the next chapter, the answer involves a choice that can be made after the particle has already finished its journey. A photon has already flown through the apparatus. It has already hit the screen. The experiment is over. Then a scientist flips a switch, and the photon's past behavior changes. This is called the delayed choice quantum eraser, and it is one of the strangest experiments ever performed. The basic idea is simple to describe and impossible to picture. You take pairs of entangled photons, send one through a double-slit setup, capture the other for later, detect the first one on a screen. Then, only after that first photon has been recorded, you decide what to do with its partner. You can either read which slit it came from, or you can erase that information forever. When you erase the path information, the interference pattern appears in the data from the first photon. When you keep the path information, the pattern vanishes. The first photon's behavior, recorded earlier, depends on a choice made later. The choice happens after the event it seems to influence. Picture a security camera that filmed an empty street last Tuesday. Then, today, someone walks through a doorway in a different city. And when you go back and watch Tuesday's footage, the empty street now shows that same person walking by, even though the camera recorded nothing at the time. That is the kind of effect we are describing. Not metaphor, measurement. For decades, people read this as proof that the future reaches into the past. Some called it retrocausality. Others called it impossible and demanded a better explanation. Most physicists now interpret it as a more nuanced illustration of quantum correlations and post-selection, with the total raw data showing no simple backward-in-time effect. Here is the cleaner story. The first photon screen on its own shows no pattern at all, just a blur. The pattern only emerges when you sort the data based on what happened to the partner photon. The information has to be matched up pair by pair before the stripes can be seen. So the past is not really being rewritten. It is being revealed in groups, depending on what you measured second. That still does not make it normal. It still means that two entangled photons share a connection that does not respect time the way we do. One photon's role in the story is decided by what happens to the other, even if that decision comes much later. Physicist John Wheeler dreamed up an even wilder version. He pointed out that the same trick could be done with light from a galaxy 10 billion light years away. A quasar's photon might have left during the early universe, traveled across half the known cosmos, and only when it reached Earth would scientists decide whether it had taken one path or two through a gravitational lens. Wheeler called this the cosmic delayed choice, and it has been quietly tested. The results match the quantum prediction every time. This means the universe does not commit to a definite history until the right measurements are made. What a particle did billions of years ago can hinge on what we choose to do today. Whether or not you call that retrocausality, the implication is unsettling. The past is less fixed than we thought. And as you're about to learn in the next chapter, that connection between separated particles is even stranger than the time problem suggests. Two particles, born together, are pulled apart. One is left in a lab in Cebu. The other is shipped to a lab in Madrid, more than 7,000 miles away. A scientist measures the first one and instantly knows the state of the second. Not after the signal travels. Instantly. This is quantum entanglement. Einstein hated it. He called it spooky action at a distance and spent the rest of his life trying to prove it was wrong. Every test since has proven it real. When two particles become entangled, their properties are tied together by a thread we cannot see. Measure the spin of one, and the other's spin is fixed in the same moment, no matter the distance. Across a room, across a continent, across the solar system. The link does not weaken with distance. It does not slow down. It does not care about miles. The key word here is correlation. The particles always agree, even though nothing seems to pass between them. Although this correlation appears to happen instantaneously, it cannot be used to send information faster than light. The universe somehow allows the connection while forbidding the use of it as a phone line. In 2025, an experiment at the National Institute of Standards and Technology used entangled photon pairs to generate truly random numbers. The detectors sat 184 meters apart. In a 30-minute run, the system recorded over 6,000 entangled photon detections. The chance that classical physics could explain the results came out to about 1 in 170 million. Past the threshold, scientists used to declare a true discovery. The link was real. Picture two coins that have been somehow welded by an invisible string. Flip one in Tokyo. It comes up heads. The other coin, sitting silent in a vault in Cape Town, also flips heads at the same instant. You did not touch it. Nobody touched it. It just knew. Einstein argued there must be a secret variable hiding inside each particle, telling it how to behave when measured. A hidden cheat sheet. In 1964, a physicist named John Bell proved this idea could be tested with a simple math inequality. If hidden variables exist, certain measurements must obey his rule. If they violate his rule, no hidden variable can save us. Experiment after experiment violates Bell's inequality. Nature breaks the rule every single time. There is no hidden cheat sheet. The link between entangled particles is something more fundamental than information passing through space. Stranger still, in 2025, researchers showed quantum non-locality without using entangled particles at all. By making four photons indistinguishable by their paths, they created non-local correlations that could not be explained by classical physics, and defied the Bell inequality threshold. The spookiness, it turns out, runs even deeper than Einstein feared. What does this mean for reality? It means that 2 points in space, no matter how far apart, can share a single quantum identity. The particles are not really two things sending signals back and forth. They are one thing, smeared across distance, behaving as a unified whole. Space, in some sense, may not be what it appears. Distance may be a story we tell ourselves about a universe that, underneath, is more woven than separate. Up next, we look at what happens when these strange particles meet a barrier that should be impossible to cross. A particle slams into a wall it does not have the energy to break. Logic says it bounces back. Reality says it sometimes passes straight through, not by force, not by speed, by breaking the rules of where it is allowed to be. This is quantum tunneling, and it is happening right now, inside your body, inside the sun, inside every transistor in the phone or laptop you are listening on. Here is how it works in the simplest terms. A particle has a certain amount of energy. Place a barrier in its path that requires more energy to climb. In our world, the particle stops. It cannot get over the wall. But in the quantum world, the particle's location is a wave of possibilities. Most of that wave reflects off the wall. A tiny piece of it leaks through. Sometimes, the particle ends up on the other side without ever having climbed over. It is as if a ball rolled at a hill too steep to climb. Most of the time, it rolls back. But once in a great while, the ball is suddenly sitting at the top. Not by jumping, not by digging, just by being where it should not be. The sun runs on this trick. Hydrogen nuclei inside the sun repel each other with enormous force. By the rules of classical physics, they do not have enough energy to slam together and fuse. The sun should not shine, yet it does. Because once in a rare while, a hydrogen nucleus tunnels through the barrier, fuses with another, and releases the burst of energy that warms our planet. Every photon hitting your skin from the sky is a record of a barrier that should not have been crossed. In late 2025, 3 physicists won the Nobel Prize in Physics for showing that this tunneling effect works even at large scales, inside electrical circuits. John Clark, Michel Devoret, and John Martinez received the 2025 Nobel Prize for their discovery of macroscopic quantum mechanical tunneling and energy quantization in electrical circuits. They proved that a current of billions of electrons could behave like a single quantum particle and tunnel through a barrier as one. The quantum strangeness was not stuck in the realm of atoms. It's scaled up. This is the foundation of every quantum computer being built today. Without tunneling, qubits do not work. Without qubits, the future does not happen. There is a darker side to this trick. Tunneling has a time problem. When a particle goes through the barrier, how long does it spend inside? Some experiments suggest the answer is shorter than light should allow. Photons appear to cross thin barriers faster than they could travel the same distance in empty space. This does not break relativity, because no usable information moves faster than light. But it hints that what happens inside a barrier is not bound by the rules outside it. Inside the wall, the particle's behavior is something we cannot fully name. It is not classical motion. It is not even normal quantum motion. It is something in between, and we do not have the right language for it yet. Tunneling shows that even solid walls are statistical illusions. Nothing is fully closed. Everything is, in some small way, porous to the strange. But what comes in the next chapter pushes the weirdness even further. What if no measurement anywhere is ever truly final? In a laboratory, a tiny object hangs in a vacuum. According to every detector in the room, the object is in 2 contradictory states at once, spinning one way and the other way. For a normal particle, this state would last a fraction of a second. This object held it for 1,400 seconds, almost a half hour. This is the modern version of Erwin Schrödinger's most famous thought experiment, the one with the cat that is supposedly both alive and dead inside a sealed box. Schrödinger came up with this scenario in 1935 to mock what he thought was a ridiculous interpretation of quantum mechanics. The joke turned out to be on him. Real cats stay one or the other, but quantum cats, made of careful arrangements of atoms and photons, can be coaxed into the impossible state and held there. The reason this matters is decoherence. Decoherence is the name physicists give to the process by which a quantum object loses its weird superposition and becomes a normal classical object. Every time a quantum system bumps into the air, into light, into heat, into anything, a little piece of its weirdness leaks away. Faster than you can blink, the superposition collapses into one definite state. That is why we never see cats half dead in real life. The environment kills the magic. To keep a quantum cat alive, you need a vacuum so deep, no stray atom can touch it. You need temperatures so low, no heat can wiggle it. You need shielding so thorough, no photon can sneak in. Build that, and the impossible becomes routine. In 2024, scientists pushed the size record by creating a quantum cat state inside a sapphire crystal weighing about 16 millionths of a gram. That sounds tiny. By quantum standards, it is enormous. The crystal vibrated in two opposing patterns at the same time, like a bell that was ringing and silent at once. Picture a swing in a playground. In normal life, the swing is moving forward or moving backward, not both. In the quantum cat experiment, the swing was caught doing both at the exact same instant, and the team could measure the proof. The 23-minute record was set with a single trapped electron, isolated almost perfectly from its surroundings. The longer scientists can hold a superposition alive, the closer we get to building computers and sensors that exploit the weirdness directly. A quantum computer is, in some sense, a Schrödinger cat that has been trained to do math while it is still in the box. There is something philosophically heavy here. If a 16 microgram crystal can be in two states at once, why not a gram of metal? A kilogram of metal? A human brain? Modern experiments have placed molecules of 2,000 atoms and tiny vibrating membranes into superposition states. Suggesting the boundary between the quantum world and the classical world is not a sharp line, but a gradient defined by isolation. In other words, there is no wall between the two worlds. There is only a curtain of disturbance we cannot fully pull aside. If you could isolate anything perfectly enough, the quantum rules might apply to it, including the cat, including you. Which raises the question waiting in the next chapter. If the act of observing collapses these states, what counts as an observer? And can two observers ever truly disagree about what is real? Inside a sealed laboratory, a physicist named Alice measures a particle. She sees a definite result. She writes it in her notebook. Outside the lab, another physicist named Wigner cannot see in. To him, Alice and the particle together exist in a superposition. Two records of the same event. Both correct. Both contradicting each other. This is the Wigner's friend thought experiment, and it is the cleanest demonstration that what we call reality might depend on who is doing the looking. Eugene Wigner proposed this scenario in 1961. For decades it was just a brain teaser. Then, in 2019, a research team performed a real version using photons standing in for the observers. Their results confirmed what the math predicted. The friend concludes the quantum state has collapsed into a single state, while Wigner maintains the full quantum state is still in superposition until he measures it. The disagreement is not a mistake. It is built into the theory. Think of it this way. Imagine your friend opens a present at her birthday party. To her, the gift is now a known thing. She has seen it. But to you, sitting outside the building, the gift is still wrapped, still unknown. Now extend that to the quantum world. To Alice, the particle is one thing. To Wigner, Alice and the particle together remain undecided until he opens the lab door. Both are right, about the same event. This is unsettling because it suggests that facts are not always universal. What looks like a settled outcome to one observer can look like an open possibility to another. The math allows this. Experiments support this. Yet our intuition rebels. A few interpretations of quantum mechanics make peace with this in different ways. The many worlds interpretation says the universe splits at every measurement. Alice's branch contains one outcome. Wigner's analysis covers both branches at once until he checks. Neither is wrong. They are looking at different slices of a multiverse. The cubist interpretation says quantum states are about what an observer knows, not about what is. Alice's collapse is her update of personal belief. Wigner's superposition is his lack of information. There is no contradiction because there is no observer-independent reality being described. A third view, the relational interpretation championed by Carlo Rovelli, says reality itself is relational. Properties exist only in the context of an interaction between systems. The particle's state is not a thing the particle has on its own. It is something that exists between the particle and whoever measures it. A more recent extension, the Fraukiger-Renner paradox, pushed Wigner's idea harder. It set up a scenario in which three reasonable assumptions about quantum measurements lead to a logical contradiction. To escape, at least one assumption has to be dropped. Which one? That depends on which interpretation you favor. There is no neutral answer. What this means in plain terms is shocking. The idea that the universe has one definite description that all observers must agree on may simply be false. Different observers, doing their jobs correctly, can hold incompatible records of the same event without anyone being mistaken. Reality, at its base, may be perspective-bound. You can probably feel the ground shifting. Solid objects are clouds of possibility. Choices made now can shape what we say happened before. Two truthful observers can describe the same event in conflicting ways. And in the next chapter, we discover what happens when one of those particles tries to pretend it has no history at all. 4 photons enter a tangled web of mirrors and crystals. By the time they leave, no measurement on Earth can tell which photon came from where. Their origins are not just unknown, they are erased. And in that moment, the particles do something they should not be able to do. In late 2025, a team of physicists ran this experiment and reported a result that shook a foundation of quantum theory. They produced the kind of spooky correlation Einstein hated, the kind usually seen only between entangled particles. But the photons in this setup were explicitly not entangled before their detection, and the spookiness came from quantum indistinguishability rather than entanglement. For decades, the textbook story said that non-local effects, the ones that violate Bell's inequality, only happened with entangled particles. Entanglement was the only door to this strange behavior. Now there is another door, and it opens when particles can no longer be told apart. Imagine 4 runners crossing a finish line at the exact same moment, wearing identical clothes, with no cameras able to track their paths. You cannot say which one came from lane 1 or lane 4. They have lost their individual histories. In this experiment, the photons lost theirs in the same way. When the experimenters could not, even in principle, trace a photon back to its origin, the photons started showing correlations that should have been impossible. This is more than a curiosity. It tells us something deep about what quantum mechanics actually requires. The strangeness does not need a previous physical link. It needs only the absence of which path information. The minute identity is erased, possibilities rearrange themselves. Picture a deck of cards. Normally every card has a face value, but what if the cards were shuffled so perfectly that any one of them could legitimately be any value until you turned it over? In that case, the probabilities of the whole deck would behave strangely. Each card's identity is suspended. When you finally peek, the values settle. But the patterns in how they settle can show correlations no normal deck could produce. The team used a laser to fire photons through a specially designed crystal. They arranged paths so cleverly that any one of 4 photons could have come from any one of the source points. Under the precise experimental conditions, the photons produced could not be traced back to a specific origin point, and there was no which path information available. With that, Bell's inequality fell apart in the data. The classical world had no way to explain what came out. The authors are careful. They admit the experiment has loopholes that need closing before this becomes ironclad. But the core finding stands. Indistinguishability alone can power the same non-local behavior we thought required entanglement. What does this say about reality? It says that the universe is sensitive not only to what particles are, but to what we can know about them. When even the universe itself cannot tell which particle is which, the rules shift. Identity in physics may be more like a setting than a fact. Turn that setting off, and possibilities mix in ways our intuition cannot follow. This pushes a haunting idea forward. Maybe the world we see is not built from objects with fixed identities. Maybe it is built from patterns that look like objects only when our measurements force them to. Up next, a single particle decides to be in two places at once, then refuses to choose even after it should have. A single atom is placed in a trap. A laser pulse splits its state in half. Now the atom is in two energy levels at the same instant. Excited and grounded. Up and down. Both. Until something forces the choice. This is not a thought experiment. It is the working principle behind every atomic clock that runs your global positioning system. Every time you check your phone for directions, you are relying on atoms held in superposition long enough to count time more accurately than any mechanical device ever could. The atom in the clock is usually cesium. It has two specific energy states. A microwave field tickles it into a superposition of both. Then a probe checks how many atoms ended up in each state. The frequency of the microwave that produces the most evenly mixed result is the definition of 1 second. We have built our entire system of time on the wobble of an atom that cannot decide what it is. Inside that suspended state, the atom is not split. It is not flickering between two options. It is in a genuine quantum mixture. The math describes one wave function that includes both possibilities, with specific amplitudes assigned to each. Neither possibility is more real than the other, until the measurement happens. Imagine a violin string that, while vibrating, somehow plays two notes at once, not as a chord, but as a single sound that is both notes and neither. You cannot hear that in a concert hall. But the atom does this with energy states. And 1,000 of these mixed atoms in a vacuum chamber define the most precise clock on Earth. Newer atomic clocks use a different element called ytterbium and exploit even subtler superpositions. The best of these clocks would not gain or lose a second over the entire age of the universe. Their precision is so extreme that they can detect when you lift the clock by 1 centimeter, because gravity at that slightly higher altitude pulls a fraction less, and time ticks a fraction faster up there. Quantum superposition lets us see time bending under the lightest touch. This is where it gets philosophical. If the atom in the clock is in a superposition for a fraction of a second, what is the atom doing during that fraction? Is it really both states at once, smeared like a wave? Or is one of them the true state and the other an illusion of incomplete information? The instrumentalist answer says, it does not matter. We can predict the clock's behavior with stunning accuracy, whether we treat the superposition as real or as a useful fiction. The clock works, the phones work, the satellites work. The realist answer is harder. If the superposition is real, then for that brief slice of time, the atom occupies a state that no language really captures. It is not a blur of motion or a swap between options. It is a genuine ambiguity in the structure of the world. The same ytterbium atom, untouched by any human, is doing this naturally inside the Earth's crust right now. The behavior is not a human trick. It is what atoms do when nothing is forcing them to commit. What you should sit with is this. Every accurate timekeeping device on this planet runs on a phenomenon that violates common sense. Time itself, as we measure it, is built from indecision. In the next chapter, the indecision spreads further. We meet particles that scientists have never seen, but that may be hiding in 2 dimensions of space, breaking the rules of identity itself. Every particle ever found in the universe falls into one of 2 clubs. Fermions, the loners, like electrons and quarks. Bosons, the socialites, like photons and gluons. For 100 years, these were the only options on the table. Then physicists asked a heretical question. What if there was a third kind? In 2025 and 2026, the answer started arriving. Researchers may have just cracked open a hidden side of the quantum world. For decades, every known particle was thought to belong to one of two categories, bosons or fermions. But researchers have now discovered new quantum particles that break those rules. These new entities are called anyons, and they live in a place where reality is flatter than we thought. To understand why anyons are strange, start with the two old clubs. Fermions, like the electrons in your fingertips, refuse to occupy the same state. Stack two electrons together in the same orbital and they push each other away. This is the rule that gives matter its solidity. Bosons do the opposite. Photons can pile into the same state as much as they want. That is why a laser works. When you swap two identical fermions, the math gives a negative sign. When you swap two identical bosons, the math gives no change. These are the only two options in three-dimensional space. The math is forced. Drop to two dimensions though, and the rules loosen. In a flat universe, you can swap two particles, and the math can give any rotation, not just a plus or a minus. Particles in two dimensions can be neither fermions nor bosons. They can be anyons. The name was a joke. Anyons. They can be anything. Anyons have been theorized since the 1970s. They have been used to explain strange behavior in flat sheets of cooled materials where electrons get pinned into two-dimensional motion. In May 2025, a team at the Okinawa Institute of Science and Technology proved theoretically that one-dimensional anyons could exist and be detected through their momentum patterns. The experimental tools to see them, they said, are already in laboratories around the world. Why does this matter for reality? Because anyons remember their history. When you swap two anyons, the act of swapping leaves a trace, like a knot tied around their identity. Swap them again in a different order, and you get a different result. This is called non-abelian statistics. Particles whose past braiding determines their present state. Picture two threads on a loom. Twist them around each other once, then again in a different direction. The resulting pattern depends on the order of the twists. Anyons behave like that, except the threads are particle paths through space and time. This is more than a curiosity. Anyons are the building block of a proposed quantum computer that would be almost immune to error. Information could be stored in how the anyons are braided. A passing particle of dust would not break the code, because the braiding pattern is a topological feature, robust against small disturbances. Companies are racing to build such machines. If they succeed, anyons go from theoretical curiosities to the heart of a new technology. But the deeper lesson is about identity. In three dimensions, particles are simple. They are either gregarious bosons or aloof fermions. Drop a dimension, and the universe permits a richer kind of identity, one that depends on history. The very category of what kind of thing this is turns out to be flexible. The next chapter takes the flexibility further. What if a particle does not just remember its braiding, but its entire history, and uses that memory to behave in ways that defy every measurement we make on its present? Empty space is not empty. Right now, in the gap between your hand and the screen of your device, particles are popping into existence and vanishing again. Trillions of them per second per cubic inch. They are too brief to be caught directly, but their effects can be measured. And those effects mean the universe has memory at the most basic level. This is the quantum vacuum, and it is the strangest substance in physics. In classical thinking, a vacuum is nothing. Pull every atom out of a box, and what remains is empty. Quantum theory disagrees. Every field that fills space, the electron field, the photon field, the various other fields whose names physicists argue about, has a minimum energy. That minimum is not zero. It is a low, jittering hum. Energy fluctuates up and down constantly. Where energy fluctuates, particles can appear, exist for an instant, and disappear before any tool can catch them. These fleeting particles are called virtual particles. Some scientists prefer to call them quantum fluctuations to avoid claiming they are quite as real as the particles we measure. The debate over what they are is alive. The evidence that something is happening is not in doubt. The clearest proof is something called the Casimir effect. Place two flat metal plates very close together in a vacuum. They will be pushed toward each other, even though no air is between them and no charge is on them. The reason is that the virtual particles in the space outside the plates can fluctuate at all wavelengths. The virtual particles between the plates can only fluctuate at certain wavelengths, because the plates form a kind of resonance box. The outside has more activity than the inside. The pressure pushes the plates together. This force has been measured countless times. It is real. Picture two ships floating side by side on a choppy sea. Waves outside the ships push hard. Waves between the ships are smaller because they have less room to grow. The ships drift toward each other. Same idea, with particles instead of water. Another consequence of the vacuum's strangeness is the Lamb shift. When you carefully measure the energy levels of a hydrogen atom, they do not quite match what simple equations predict. The discrepancy is tiny, but it is exactly the size that the vacuum's jitter would cause, nudging the electron around inside the atom. Without quantum fluctuations, the atoms in your body would have slightly different energies, and chemistry as we know it would not exist. The vacuum also remembers. Pull a strong magnet through empty space, and you can leave the vacuum slightly more electrified than before. Pump a laser through a transparent medium, and you can change the optical properties of the next pulse. These effects are subtle, but they show that space is not a passive backdrop. It carries information. There is a darker, theoretical side. Some physicists believe the entire history of the universe might be encoded in the patterns of vacuum fluctuations, similar to how a hologram stores a full image on a flat sheet. If that idea, called the holographic principle, holds, then everything you have ever done is, in some twisted sense, written into the spaces between atoms. What you should take from this is that nothing is ever empty. The universe is built on a foaming, restless substrate that we can poke but never empty out. Pull every particle out of a region of space, and the region still hums. And as you will see in the next chapter, that humming might be the very thing that produces the reality we see at all. A grainy security tape from a parking garage in your town contains far less information than the live scene it recorded. Now, imagine the reverse. Imagine the entire scene inside a room, every wall, every chair, every person, was actually a projection. The real data lived on the surface of the room's walls. The three-dimensional world was just a clever rendering of two-dimensional information. This is the holographic principle, and it is one of the strangest serious ideas in modern physics. The principle came out of work on black holes in the 1970s and 80s. Physicist Jacob Bekenstein noticed that the amount of information you could pack into any region of space is not proportional to its volume, as you might expect. It is proportional to its surface area. Stephen Hawking refined the idea. Two-dimensional surface, three-dimensional volume, same data limit. A bucket holds water by volume. A black hole holds information by area. Physicists then asked the wild question: what if the relationship is not just for black holes? What if every chunk of space in the universe works this way? In 1997, Juan Maldacena proved a precise mathematical version of the idea. He showed that a certain kind of universe with 5 dimensions could be exactly described by a theory of particles living on its 4-dimensional boundary. The interior was the hologram. The boundary held the real data. Picture a snow globe with a tiny city inside. The city looks 3-dimensional. You can walk through its streets in your imagination. Now flatten everything onto the glass surface. The city is still there, encoded in the patterns on the glass. The 3rd dimension was never an extra ingredient. It was a way of organizing information that already lived on the surface. If our universe works that way, The room you sit in right now, with all its depth and texture, may be a projection of information stored on a distant boundary. We do not feel the boundary, we feel the projection. The boundary is the actor's stage. We are the play. This is not just hand-waving. The math works in specific test universes that physicists can model on computers. In our actual universe, the math is harder, but several lines of evidence suggest the principle holds in some form. Calculations of black hole entropy. The way information seems to spread across the surface of a region during quantum processes. The behavior of gravity itself, which becomes much easier to describe holographically. There is even a serious proposal that gravity, the force that pulls you to the chair, is not a real force at all. It is what we feel when the holographic information rearranges itself. Things fall together because the underlying data prefers them to fall together. Mass is just a kind of error correction in the holographic code. If true, this changes how we should think about everything. Space is not a container. It is a representation. The 3 dimensions we move through are a user interface. Behind it, the real architecture is something flatter, simpler, but holding all the same content. What does this mean for the question of a reality? It means that solidity, distance, even the feeling of moving through space may not be fundamental features of the world. They may be useful approximations. Underneath, the universe may be more like a screen than a sculpture. Up next, we look at what happens when this strange foundational structure interacts with something we have not yet introduced: time itself. A quantum particle does not wear a watch. It does not check the time. It does not know when its experiment began or when it will end. The strange truth is that, at the deepest level, the laws of quantum mechanics may not need time at all. This is the timeless quantum problem, and it is one of the most uncomfortable corners of modern physics. The conflict comes from trying to combine quantum theory with general relativity. Quantum mechanics treats time as a background. Everything ticks forward at a steady rate while particles wiggle and waves evolve. General relativity treats time as part of the fabric of space, bendable and stretchable by gravity. The 2 theories disagree about what time fundamentally is. When you try to write down a quantum theory of gravity, the time variable often drops out of the equations entirely. What remains is a static description, a frozen picture, no clock ticking anywhere. This is called the problem of time, and it has bothered physicists for decades. One proposed solution is called the Page-Wouters mechanism. It says that time is what emerges when you carve a larger, timeless system into 2 pieces, one called the clock and one called the rest of the world. The rest of the world appears to evolve, relative to the clock. But the whole system, the clock plus the world, is static. Time is not something the universe has. It is something that appears when you split the universe into observer and observed. Picture a long photograph of a race. The image is frozen. But if you put your finger on one runner and slide it from left to right, that runner appears to move relative to the others. The motion is real to you, but the photograph itself is not changing. Quantum time may work like this: static when seen from outside, flowing when felt from inside. There is experimental support for this idea, at least in toy systems. Researchers have built setups using photons where one photon serves as a clock and another serves as the system. They can show that mathematically the 2 photons are in a single entangled state with no time variable. Yet from the perspective of the clock photon, the other photon evolves. Time is born from the relationship. This is a strange place to land. It suggests that the flow of time, the most basic feature of human experience, may not be a feature of the universe itself. The universe may simply be. We carve it into past and future because we sit inside it and need a way to organize what we perceive. There is more. Some quantum experiments suggest that the order of events is not always fixed. In specific setups, 2 operations can be performed on a particle in a superposition of orders. The first operation happens before the second in one branch and after the second in another branch. Both happen at once. In the quantum sense, the particle leaves the apparatus carrying the imprint of an order that is itself undetermined. This is called indefinite causal order. It has been demonstrated with photons. The implications are wild. The very notion that A causes B may, in some quantum settings, be a fluid thing. Cause and effect, like position and identity, may be observer-dependent. If time is not fundamental and cause is not fixed, what is left to anchor our sense of reality? The next chapter offers a possible answer, or a deeper problem. Every quantum measurement has multiple possible outcomes. The wave of possibilities collapses into one, the others vanish, or so the standard story goes. But there is another story, equally consistent with the math, in which nothing ever vanishes. Every possibility happens. The universe splits. And right now, countless copies of you are reading countless versions of this script, each having made slightly different choices today. This is the many worlds interpretation, proposed by Hugh Everett in 1957, and it is taken seriously by a growing number of physicists. The standard interpretation of quantum mechanics, called the Copenhagen interpretation, says the wave function collapses upon measurement. One outcome becomes real, the rest disappear, as if they never existed. But the math of quantum mechanics has no collapse in it. The Schrödinger equation just evolves wave functions smoothly forward in time. Collapse is added by hand to match what we see. Everett asked the obvious question: what if we do not add collapse? What does the math say happens? The answer is unsettling. The math says all outcomes happen. The observer and the system entangle. Each outcome lives in its own branch of a now massive wave function. The branches do not interact, because they are no longer coherent with each other. To each branch, the others are invisible. Inside each branch, there is one definite outcome. From outside, looking at the full wave function, there are many. Picture a tree growing from a single seed. Every choice you ever made was a fork in a branch. In normal life, you experience one path. In many worlds, every fork actually grew. The tree of possibilities is the real universe. You are just one twig. Many worlds removes the measurement problem. There is no special moment of collapse. There is no need to ask what counts as an observer. Everything happens. The Schrödinger equation runs cleanly. Reality just happens to be much, much larger than we thought. The cost is enormous. It requires accepting that you have an unimaginable number of cousins, all living slightly different lives, all equally real. In one branch, you stopped listening to this 5 minutes ago. In another, you became a physicist. In another, you never existed because your grandparents never met. All of those branches exist somewhere in the universal wave function. This sounds like fantasy. The math, though, is the cleanest of any interpretation. Many worlds requires no extra postulates. It only requires taking the Schrödinger equation seriously and refusing to add a collapse mechanism. There are problems. How do we recover the probabilities we observe? In any given experiment, certain outcomes happen more often than others. If every outcome happens in some branch, why do we experience the more probable ones with the right frequency? This is called the probability problem, and proponents have offered several answers. None are universally accepted. The debate continues. Many worlds is not provable in the usual sense. The other branches, by construction, are inaccessible. We cannot send a message between them. We cannot test their existence. We can only ask whether the interpretation is consistent and parsimonious. It is consistent. Whether it is parsimonious depends on whether you count branches or postulates. If many worlds is right, the strangeness we have been exploring is no strangeness at all. Particles take both paths because they take both paths, in different branches. Cats are dead and alive in different branches. Quantum non-locality is not spooky. It is just the appearance of correlations between branches that overlap until they decohere. In the next chapter, we step back and ask whether any of these interpretations capture what is really happening, or whether the right answer might be stranger than all of them. A physicist named Carlo Rovelli looks at the puzzle of quantum measurement and offers a different solution. He does not split the universe. He does not call on hidden variables. He does not invoke conscious observers. He says something simpler and more radical. There are no observer-independent facts. This is the relational interpretation of quantum mechanics, and it strips reality down to its bare bones. Ravelli's idea is that quantum states do not describe how a system is. They describe how a system is relative to another system. When two systems interact, each acquires properties relative to the other. There is no absolute property hiding underneath. There is no view from nowhere. Reality is a web of relationships. Picture two dancers on a stage. From one dancer's frame of reference, the other is to her left. From the other's frame, the first is to her left. There is no fact about who is really on whose left. In some absolute sense, the relationship is the reality. Now extend that to every property in physics. Position, momentum, spin, energy, all of them on this view are relational. This sounds abstract, but it solves several puzzles at once. Wigner's friend disagreement disappears. Of course, Alice and Wigner have different states for the particle. They are describing different relations. Alice's measurement gives the particle a property relative to her. Wigner has not yet interacted with the system. So for him, the property is not yet defined. Both descriptions are correct. They are not in competition. The collapse of the wave function also stops being mysterious. There is no global collapse. There is only the update of relations between specific systems when they interact. To Alice, the particle has a definite spin after she measures it. To Wigner, who has not interacted, that definiteness is not yet a relational fact for him. There is no contradiction because there is no single universal state being described. Entanglement in this view is the most natural thing in the world. Two particles are entangled when their relation has been established. Distance does not matter because relations are not transmitted through space. They are just there. The connection is not spooky. It is what it means for two systems to share a history. What you give up to gain this clean picture is the idea of an underlying objective reality. The universe stops being a stage with actors. It becomes a network of interactions. Each interaction is a tiny update in the web. The web is the only thing. There is no scenery behind it. Some philosophers find this liberating, others find it terrifying. If there is no absolute fact about how things are, what stops physics from sliding into pure subjectivity? Ravelli's answer is that the web is shared. Two observers, when they interact, will agree on their relational descriptions of each other. Different perspectives are not arbitrary. They are constrained by the structure of the network. This is, in some ways, very close to how relativity treats space and time. Einstein showed that there is no absolute simultaneity. Two events that are simultaneous for one observer are not simultaneous for another. Both are right. Both describe valid frames of reference. Ravelli extends this idea down to the foundations of quantum theory. Just as time is relational in relativity, every quantum property is relational in his interpretation. Not everyone is convinced. Critics argue that the view leaves too much unsaid about what an interaction is, or what counts as a system. The framework, they say, is suggestive rather than complete. Defenders argue that the framework is exactly as complete as it needs to be. Adding more would be adding fiction. Up next, we look at what these interpretations imply when they meet the most controversial idea in physics: consciousness. Inside a sealed laboratory, a photon hits a detector. The detector clicks. The information passes through wires into a computer. The computer prints a result. A scientist walks in, picks up the printout, and reads it. At which point in this chain did the quantum superposition collapse? This is the heart of the measurement problem, and one of the most controversial answers is that consciousness itself does the collapsing. The idea is old. Eugene Wigner, the same physicist who dreamed up the Friend paradox, once suggested that the mind might be the thing that turns possibilities into facts. Nothing else in the chain, he reasoned, has the right character to do the job. Detectors are made of atoms. Atoms can be in superposition. Computers are made of detectors. They can be in superposition. The only thing in the chain that we know experiences a single, definite outcome is the conscious observer. Maybe that is not a coincidence. Maybe consciousness is the missing ingredient. This idea has been pushed by a small but persistent group of physicists. Roger Penrose, the mathematician who won a Nobel Prize for work on black holes, has argued that something in the brain, perhaps in the microtubules inside neurons, exploits quantum collapse to produce conscious thought. The collapse is not driven by the mind. The collapse produces the mind. Most physicists do not buy this. They point out that decoherence, the leaking of quantum information into the environment, can explain why we never see superpositions of large objects. A detector that records a photon is so massively entangled with its surroundings that the superposition becomes invisible almost instantly. No conscious observer is needed. The cat dies long before anyone opens the box. Decoherence is well tested. It explains a lot, but it does not, strictly speaking, solve the measurement problem. It shows why we cannot see superpositions of cats. It does not say why one outcome rather than another becomes our experience. Decoherence narrows the possibilities. It does not pick the winner. The picking is where the conscious observer interpretations sneak back in. If the universe is in a giant entangled state, and decoherence cuts it into branches that no longer interfere, what determines which branch you find yourself in? Some interpretations say all branches are real, and you exist in all of them. Others say there is a special role for the observer in selecting a branch. The honest position is that nobody knows. Picture a deck of cards spread across a table. Decoherence is the process that makes each card distinct, so the deck is no longer one shuffled pile. But which card you actually draw is still an open question. Some say all cards get drawn in parallel realities. Some say something else picks. The something else is where the mind keeps trying to enter the story. There is a recent twist. A 2026 paper in a Nature journal proposed a framework that treats the observer as an integral part of sensory information processing within entangled quantum systems. The model treats sensory data evolving via interaction with quantum-based observer states during the pre-decision phase, classified adaptively using positive operator-valued measures. The math is technical. The implication is striking. Even within mainstream physics journals, the question of the observer's role is being formalized rather than dismissed. This does not prove consciousness collapses the wave function. It does mean the topic is not closed. The question of why one outcome rather than another becomes my experience is still on the table after 100 years of trying. What you should keep in mind is that the deepest mystery of quantum theory may not be about particles at all. It may be about what it means to be the kind of system that records a definite result. In the next chapter, we leave the brain and head into the realm where these strange laws begin to shape the engineering of the future. A processor sits inside a refrigerator colder than outer space. It is the size of a small chandelier. Wires drop into it from above. Inside, less than 100 tiny pieces of metal hover at almost absolute zero, in a state that is not on, not off, but both. This is a quantum computer, and it is starting to do things no classical machine ever could. The basic building block is the qubit. A normal bit is a 1 or a 0. A qubit can be a 1, a 0, or a superposition of both at the same time. Stack 100 qubits together, and the machine holds an enormous number of possible states at once. It explores them in parallel. Then, with a careful sequence of operations, it amplifies the right answer and cancels out the wrong ones. When you read the qubits at the end, the answer falls out. In 2025, the Nobel Prize in Physics went to the team whose work made this possible. John Clark, Michael Devereux, and John Martinez received the prize for their discovery of macroscopic quantum mechanical tunneling and energy quantization in electrical circuits. That work showed that whole electrical circuits carrying billions of electrons could behave like single quantum objects. Their circuits, called superconducting qubits, are now the foundation of quantum computers built by companies whose names you would recognize. These machines are not faster at everything. They are not going to replace your phone. They are tools designed for specific problems where the superposition advantage matters. Factoring giant numbers, searching huge unsorted databases, simulating molecules for new drugs or materials. Each of these tasks, for a classical computer, scales badly. For a quantum machine, the scaling is gentler. Picture a maze with 1,000,000 paths. A classical computer walks down each path one at a time, checking for the exit. A quantum computer sends a ghostly version of itself down every path at once. And when the right paths interfere correctly, the answer emerges. The trick is not just exploring all paths, it is making the wrong ones cancel out. So you can read the right one without noise. That trick is fragile. Every qubit must remain in superposition long enough to complete the calculation. Every interaction with the environment, every stray photon, every tiny vibration threatens to collapse the qubit into a definite state too soon. This is why the machines live in refrigerators and shielded chambers. The quantum world is delicate. Error correction is the next frontier. By cleverly entangling many physical qubits into a single logical qubit, scientists can detect and fix the errors caused by environmental noise. The math is heavy. The results are getting better. Several companies are racing to build a fault-tolerant quantum computer, a machine that can run long calculations without losing its quantum coherence. When that machine arrives, the consequences will reach into ordinary life. Modern internet security relies on the difficulty of factoring large numbers. A quantum computer that can factor those numbers will break most current encryption in a fraction of a second. Governments are already preparing post-quantum cryptography, new codes that resist quantum attack. The arms race has begun. Drug discovery may be transformed. Simulating how a candidate molecule binds to a protein requires solving the full quantum mechanics of dozens or hundreds of atoms. Classical computers can only approximate this. Quantum computers made of the very same kind of physics could simulate it exactly. New medicines, new materials, new energy storage technologies might pour out of these machines. The strangest part is that the entire technology rests on the same strangeness that started this script. Superposition, entanglement, measurement collapse, the very oddities that make reality hard to trust, are the engine behind the next century of computing. In the next chapter, we look at what happens when these machines start to talk to each other, across continents, using particles that share a connection no signal can break. A message leaves Beijing. It arrives in Vienna. Nobody, not even with infinite computing power and infinite time, can read it without alerting the sender. This is not a thought experiment. A working version of this technology was demonstrated in 2017, and the network has been growing ever since. The science behind it is called quantum key distribution. Two parties who want to share a secret use entangled photons or single photons in carefully chosen states. The sender encodes random bits in the polarization of each photon. The receiver measures them. Then they compare a small portion of their results over a normal channel. If anyone tried to intercept the photons, the act of measurement would have disturbed them. The error rate would spike. The eavesdropping would be detected. This is not better encryption. It is encryption guaranteed by the laws of physics. The thief cannot succeed without breaking quantum mechanics itself. In recent years, China has built a fiber optic quantum network connecting Beijing, Shanghai, and several other cities. A satellite called Misius has demonstrated quantum key distribution between ground stations more than 7,000 miles apart. Europe is building its own quantum internet testbed. The United States has several research networks running. The technology is real, and it is scaling. Picture a sealed envelope made of soap film. If anyone touches it to peek inside, the bubble pops. Quantum communication is like that, but the bubble is woven from the rules of physics. Touch the message, and the message changes. The change is detectable. The interception fails by definition. There is another piece to the puzzle called quantum teleportation. The name is misleading. Nothing physical is teleported. What is teleported is a quantum state. If Alice has a particle in some unknown quantum state, and she shares an entangled pair with Bob, she can perform a clever measurement on her particle and the entangled one. The result of her measurement, sent through a normal channel, lets Bob reconstruct the unknown state on his end. The original is destroyed. The state has hopped from one place to another without traveling through the space between. This has been done with photons, with atoms, with small clusters of ions. The current record for distance is over 800 miles. The state moves. The matter does not. Quantum teleportation is essential for a real quantum internet. Without it, you cannot stitch together quantum computers across cities. With it, you can. Imagine a network of quantum machines, each handling part of a calculation, sharing entangled states the way today's internet shares packets. The combined power would dwarf any single machine. There are limits. Quantum teleportation requires a classical channel for the measurement results. Information still cannot move faster than light. The connection is instantaneous in the entangled pair, but the message it carries needs a slow signal to make sense. Relativity survives. Still, the social impact will be enormous. Banking, military communication, voting systems, medical records, all of them could be locked behind quantum keys that no future computer can break. Whoever builds this infrastructure first gains a strategic advantage that may not be reversible. The fragility of the quantum world, the very thing that makes it strange, is becoming the basis of the most secure communication ever invented. The same delicacy that hides Schrödinger's cat from us shields our messages from spies. The universe, in the end, may turn out to be a better engineer than any of us. Up next, we visit the boundary where physics meets biology, and ask whether life itself runs on quantum tricks. A robin in a meadow tilts its head toward the sky and turns north. It has no map. It has no compass. It has something stranger. Inside its eye, a chemical reaction is using quantum mechanics to read the Earth's magnetic field directly. The bird is, in a real sense, seeing the planet's invisible lines. This is one of the cleanest examples of quantum biology, the new field that asks whether the strange rules of the small scale matter at the scale of living things. The mechanism is called the radical pair model. When a photon strikes a special molecule in the robin's eye, called cryptochrome, 2 electrons get knocked into an unusual state. The 2 electrons are now in a quantum pair, their spins linked, but not yet locked into a definite orientation. The Earth's weak magnetic field, far too small to push around any ordinary chemistry, can subtly tilt the balance between the 2 possible spin orientations. The result of that tilt changes which chemical products form. The bird's eye reads those products as a signal. Direction emerges from quantum physics. The Earth's magnetic field is about half a Gauss. The energy it deposits on the electron pair is unimaginably tiny. Classically, it should not matter. Quantum mechanics, with its sensitivity to phase and coherence, lets the bird amplify the effect enough to use. In 2021, scientists at the University of Oxford confirmed that the cryptochrome in robin eyes does behave the way the model predicts. Other animals appear to use similar tricks. Sea turtles, monarch butterflies, certain fish. The animal kingdom seems full of quantum compasses. Picture a balanced scale so finely tuned that the weight of a single feather can tip it. The Earth's magnetic field is that feather. Quantum coherence is the precision of the scale. Classical chemistry would never feel the feather. Quantum chemistry does. Photosynthesis may be another quantum trick. When sunlight strikes a leaf, the energy must travel from the absorbing molecule to the reaction center where chemistry happens. In a classical picture, the energy would hop randomly from molecule to molecule, losing efficiency at every step. Experiments suggest the energy actually travels as a quantum wave, exploring multiple paths at once, finding the most efficient route by interference rather than trial and error. Plants may be running quantum computations to capture sunlight. The smell sense is another candidate. The classical explanation says scent molecules fit into receptors in your nose, like keys into locks. Some researchers argue this cannot explain the full range of human smell. They propose that the receptors detect the quantum vibrations of the molecule, not just its shape. The evidence is mixed. The idea is alive. Even enzymes, the proteins that drive almost every chemical reaction in your body, may use quantum tunneling. The proton or electron that an enzyme needs to move sometimes appears to pass through an energy barrier rather than over it. Without the quantum trick, the reaction would be too slow to sustain life. This raises a profound question. If life evolved to exploit quantum mechanics, then living things are not just made of atoms following classical rules. They are systems that have learned to work with the deeper strangeness of the world. The boundary between physics and biology may not be where we drew it. There are critics. Quantum coherence is famously fragile. The warm, wet inside of a cell should destroy it almost instantly. Yet the experimental evidence keeps suggesting that biology has found ways to protect quantum effects long enough to matter. How life does this remains an open question. If quantum biology is real, then every breath you take, every thought you have, every meal you digest, may rely on the same weirdness that lets a cat be alive and dead at once. The strange is not somewhere else, it is inside you. In the next chapter, we follow this thread further and ask whether the brain itself is a quantum machine. Inside your skull sits the most complicated object known in the universe: 86 billion neurons, trillions of connections, and according to a small but stubborn group of physicists and biologists, a network of microscopic structures that may run on quantum mechanics. The idea is most famously associated with Roger Penrose and the anesthesiologist Stuart Hameroff. Their proposal, called orchestrated objective reduction, claims that consciousness arises from quantum computations happening inside microtubules. Microtubules are tiny hollow tubes inside every cell, including neurons. They are part of the cellular skeleton. Penrose and Hameroff argue that they are also tiny quantum processors. The model goes like this. Microtubules contain proteins called tubulin. Each tubulin can exist in different conformations. In the proposal, those conformations can be in quantum superposition, briefly. The superposition spreads across many tubulin units in a microtubule, and across many microtubules in a neuron, and across many neurons in a region. Then, at a specific moment, the superposition collapses. That collapse, the authors argue, is the basis of a single conscious moment. This is wildly controversial. Most neuroscientists do not accept it. Most physicists are skeptical. The brain is warm and wet, and quantum coherence in such an environment seems impossible. Decoherence should destroy any quantum effect in fractions of a billionth of a second, far too fast to matter for thought. Yet evidence keeps trickling in that life can protect quantum effects in surprising places. Photosynthesis, bird navigation, enzyme tunneling. The brain might join that list. Or it might not. Picture an orchestra where every musician plays a note that is, briefly, a chord of all possible notes. Then, at a specific moment, the chord resolves into a single tone. The model says consciousness is the moment of resolution, and the chord is the quantum substrate. Recent experiments have hinted, without proving, that microtubules might support certain kinds of resonance and coherence beyond what classical models predict. The work is contested. The interpretations are debated. The mainstream view remains that the brain is a classical machine, vastly complicated but running on the same physics as any other biochemistry. Yet the quantum brain hypothesis has not died. It keeps coming back. Why does this matter? Because if consciousness depends on quantum mechanics, then the measurement problem and the mind problem might be the same problem. The thing that turns possibilities into facts in physics might be the same thing that turns brain activity into experience. One mystery would solve two puzzles. That is exactly the kind of move that physicists usually love. If the hypothesis is wrong, consciousness is purely classical. The brain is a wet computer. The fact that it produces subjective experience is still mysterious, but the mystery does not require quantum mechanics to solve. Most working scientists are agnostic. They do not see compelling evidence either way. They wait for better experiments and better theories. The honest answer to the question, is your brain quantum, is that nobody knows. The interesting thing about Penrose and Hameroff's idea is not whether it is right. It is that in the year 2026, serious thinkers are entertaining the possibility that your thoughts and the behavior of subatomic particles are linked by more than just chemistry. The conversation has moved from absurd to merely speculative. That is a real shift. What you should sit with is this. Even if your brain is not quantum, you are made of atoms that absolutely are. The boundary between mind and matter is messier than we used to think. In the next chapter, we step back from biology and look at one of the most disturbing recent ideas in physics. The idea that the universe might be running on something even stranger than quantum mechanics. Quantum mechanics is the most accurate theory in the history of science. It predicts experimental results to more decimal places than any other framework. And yet, a growing number of physicists suspect that quantum mechanics is not the final answer. They suspect there is another theory underneath it, a deeper game. The hunt for that deeper theory is one of the great quiet stories in modern physics. One direction of search is called superdeterminism. The idea is that the choices physicists make in their experiments, what to measure and when, are not really free. They are correlated with the particles being measured, because both the experimenter and the particles share a common past that determined everything in advance. If that is true, the apparent strangeness of quantum mechanics disappears. There are no spooky correlations. There is only a deeply linked universe where everything was set up to look spooky from the start. The physicist Sabine Hossenfelder is one of the most prominent defenders of this view. She argues that the experiments that supposedly rule out hidden variables actually assume something called statistical independence, which superdeterminism rejects. If you drop that assumption, hidden variables can survive. The universe becomes deterministic. The spookiness becomes an illusion. Most physicists do not accept superdeterminism. They argue that giving up statistical independence makes science itself impossible. Every experiment depends on the assumption that the experimenter can choose freely what to measure. Without that, all results become suspect. The cure, critics say, is worse than the disease. Another direction is called objective collapse theories. These add a small modification to standard quantum mechanics. They say wave functions really do collapse on their own without needing an observer. The collapse is rare for small systems and frequent for large ones. That explains why we see definite outcomes for big objects and superpositions only for tiny ones. The most famous version is called the Ghirardi-Rimini-Weber theory. Objective collapse theories make different predictions from standard quantum mechanics. Specifically, they predict tiny violations of energy conservation and small heating effects in isolated systems. Experiments are looking for these signatures. So far, nothing has been found above the precision of measurement. Either the theories are wrong or the effects are smaller than current sensors can detect. A third direction is called pilot wave theory, originally proposed by Louis de Broglie and later developed by David Bohm. In this picture, particles always have definite positions, and they are guided by a quantum wave that fills space. The wave does the spooky work. The particle just follows. This theory reproduces all the predictions of standard quantum mechanics while keeping definite particles and definite trajectories. The cost is that the guiding wave must travel faster than light, which clashes uncomfortably with relativity. Picture a surfer riding a wave. The surfer is the particle. The wave is the quantum guide. The surfer goes wherever the wave directs. There is nothing weird about the surfer. The wave does all the strange things. like sloshing in two directions at once or carrying information across distances faster than the surfer could swim. Pilot wave theory says reality is a surfer on a wild ocean. Then there are even more speculative ideas. Some physicists think space and time themselves emerge from a deeper structure of pure information. Others think the universe is a kind of self-organizing computation. Still, others argue that quantum mechanics is fundamental and the search for a deeper theory is misguided. Nobody knows which path leads to the truth. The experiments that could distinguish between these views are mostly out of reach today, but they are getting closer. Within a few decades, we may have the technology to test specific predictions of objective collapse or pilot wave theory against standard quantum mechanics. What you should take from this chapter is that the strangeness we have been exploring is not yet settled. We have the math, we do not have the meaning. The meaning is up for grabs. In the next chapter, we explore what happens when these strange particles meet the most extreme objects in the universe. A black hole sits at the center of a galaxy. It is so dense that nothing, not even light, can escape from inside its horizon. According to general relativity, anything that falls in is lost forever. According to quantum mechanics, that should be impossible. Information cannot be destroyed. The clash between these two theories has been simmering for half a century. It may be the most important unsolved problem in physics. The story starts with Stephen Hawking. In 1974, Hawking applied quantum field theory near a black hole's horizon and discovered something shocking. Black holes are not perfectly black. They radiate. Pairs of virtual particles popping in and out of existence in the vacuum get separated by the horizon. One falls in, the other escapes. The escaping particle carries energy away from the black hole. Over enormous timescales, the black hole evaporates entirely. This sounds elegant. The problem is what happens to the information that fell in. If a book falls into a black hole, and the black hole eventually evaporates into Hawking radiation, where did the book's information go? Quantum mechanics says it must still be there, encoded somehow. Hawking originally argued it was simply gone. That answer would break quantum mechanics itself. This is called the black hole information paradox, and physicists have been wrestling with it ever since. Picture a piano falling into a deep well, then the well boiling away. According to the rules of one theory, the piano's information must come back out in the steam. According to the rules of another theory, the steam is featureless. Both theories cannot be right. One of them must be wrong, or both must be incomplete. Several proposed solutions exist. One says the information escapes in the Hawking radiation, subtly encoded in correlations between the outgoing particles. Another says the information is stored on the horizon itself, in patterns we cannot yet decode. A third says black holes have a kind of soft hair, tiny structure on their horizons, that records what fell in. A fourth, called firewalls, suggests that the horizon is not a smooth surface but a wall of high-energy particles that destroys anything crossing it. In 2021 and 2022, a series of breakthroughs using string theory and the holographic principle gave the first concrete calculations showing how information might escape. The math is dense. The intuition is that information stored deep inside a black hole becomes encoded over time in the entanglement structure of the Hawking radiation. By the time the black hole evaporates, all the information is in the radiation, where it can in principle be recovered. This is, if it holds, one of the most important results in theoretical physics in decades. It does not solve every problem, but it makes the paradox tractable. The full quantum theory of gravity, when we finally have it, will likely include this mechanism as a basic feature. The deeper lesson is that quantum mechanics and gravity are not separate stories. They are different views of one underlying theory we have not yet found. String theory and loop quantum gravity are two attempts to write that theory down. Neither is complete. Both have made progress. If we ever solve this, the consequences will be enormous. We may finally understand what happens at the center of a black hole, where current theory predicts a singularity that probably is not real. We may understand the very early universe, when conditions were so extreme that gravity and quantum effects were comparable. We may even understand what existed, if anything, before the Big Bang. For now, the edge where quantum meets gravity is the frontier. Every test, every theoretical advance, brings us closer to a unified picture. The strangest possibility is that the unification will reveal a reality even less familiar than what we have already seen. In the next chapter, we follow the strangeness into the world of materials, where particles can behave like things we never expected. In a laboratory, a thin sheet of carbon is cooled to a few degrees above absolute zero. A current is sent through it. The electrons in the sheet do something unbelievable. They stop behaving like billiard balls. They begin to flow like a liquid. A perfect liquid, with almost no friction at all. In April 2026, a team announced that they had observed this exotic state in graphene. Scientists have observed electrons in graphene flowing like a nearly frictionless liquid, defying a core law of physics, an exotic quantum state that reveals new fundamental behavior and could unlock new technologies. This sounds technical. It is also incredibly strange. In a normal wire, electrons bounce around as they carry electricity. They collide with the atoms of the wire. They collide with each other. They scatter in random directions. Most of the time, the average flow is in the direction of the voltage. The collisions waste energy as heat. This is why your phone gets warm. In the new state, the electrons stop colliding randomly. They start flowing in coordinated streams, the way water flows in a river. They interact with each other so frequently and so strongly that they behave as a single fluid, rather than a bunch of separate particles. This is called hydrodynamic electron flow. It has been predicted for years. The new experiment shows it clearly. Picture a crowded subway car at rush hour. In normal conditions, everyone bumps into each other randomly, jostling left and right. The crowd warms up. Energy is wasted. Now imagine the same crowd, but everyone moves in perfect unison, sliding gracefully past each other without any bumping. No energy is wasted. The crowd flows like silk. That is what the electrons did. The implications go beyond cool experiments. If we can engineer materials that always flow electrons this way, we can build wires that lose almost no energy, supercomputers that do not require massive cooling, phones that last weeks on a single charge, electric vehicles with much greater range. This is not the only weird material behavior. Superconductors, discovered over a century ago, carry current with literally zero resistance below a certain temperature. The electrons pair up, by an effect called Cooper pairing, and the pairs move through the material without scattering. Superconductors levitate magnets, run the magnetic resonance imaging machines in hospitals, and form the basis of many quantum computer designs. Some materials show even stranger states. Spin liquids, where the magnetic spins of atoms refuse to settle into a regular pattern even at temperatures near absolute zero. Topological insulators, which conduct electricity only on their surfaces, not through their interiors. Skyrmions, tiny knots of magnetic field that behave like particles and can be moved around for storing information. Each of these states arises from quantum mechanics acting collectively across billions of atoms. The single particle weirdness of the early chapters, where one photon behaves like a wave, is amplified into the behavior of entire materials. The same superposition and entanglement that haunts the smaller scales emerges in different forms at the scale of objects you can hold in your hand. This is why quantum mechanics is not just a theory of the small. It is a theory of how reality is structured at every scale. The wires in your wall and the cells in your body and the stars in the sky all run on the same underlying rules. The rules just hide differently in different settings. A recent breakthrough has scientists studying what they called a quantum dance inside superconductors. Researchers directly imaged how particles pair up in a system that mimics superconductors, and instead of behaving independently, the pairs moved in a synchronized way. The coordination of trillions of electrons can look almost choreographed when viewed at the right scale. What you should take from this is that the quantum world is not exotic. It is everywhere. The strangeness of the very small is the foundation of everything else. In the next chapter, we ask what happens when these quantum strangeness combines with our growing ability to measure the universe with unprecedented precision. A new type of clock is so accurate that if you place two of them at slightly different heights, you could measure the difference in how fast time flows between them. The clocks lose less than 1 second over the entire age of the universe. They are reaching the limit of what can be measured, and they are running on quantum mechanics. The technology is called an optical lattice atomic clock. Atoms are trapped in a grid made by crossed laser beams. The grid holds each atom in its own little pocket of light. A second laser tickles the atoms to make them oscillate between two energy states. The frequency of that oscillation defines the tick of the clock. The current best clocks use strontium or ytterbium atoms. They can detect changes in elevation of less than a centimeter because gravity ever so slightly slows time at lower altitudes. This is the first time humans have built instruments that can directly measure the warping of time at the scale of our daily lives. Picture a pond at twilight. The surface is almost perfectly still. You drop a single grain of sand into it. The ripples are too small to see by eye. A perfectly sensitive instrument, though, can detect them across the entire pond. The new clocks are like that, except the pond is space-time and the ripples are gravity. The applications are wild. Geologists are starting to use these clocks to map the density of the Earth's crust by measuring tiny gravitational differences from one location to another. Hidden oil deposits, magma chambers, even submerged ancient ruins might be detectable by their gravitational signatures. Atomic clocks become tools for surveying the inside of a planet without drilling. Climate scientists may use them to track changes in sea level and ice mass from space. A network of orbiting quantum clocks could give us a real-time map of how Earth's mass is shifting due to climate change. We could see polar ice loss with a precision impossible today. Cosmologists are pushing in the other direction. Networks of clocks scattered across continents could form a giant antenna for gravitational waves at frequencies we cannot detect with current instruments. Whole new regions of the gravitational wave spectrum may open up. Signals from black holes too small or too large for current detectors. Whispers from the very early universe. There is more. Quantum sensors are not limited to clocks. Atomic magnetometers, using the spins of atoms as detectors, are now sensitive enough to measure the magnetic field of a single nerve cell firing in the human brain. Brain imaging without the heavy machinery of a hospital scanner. Real-time, portable, biocompatible. Quantum gravimeters use cold atoms in free fall to measure tiny variations in gravity. They have been deployed to detect underground tunnels, mineral deposits, and even buried infrastructure. As they get smaller and cheaper, they will become common tools for engineering and security. The principle behind all of these sensors is the same. Quantum systems respond to their environment in ways that are extraordinarily delicate. Push them just a little, and you can read the push with stunning precision. This is the flip side of the fragility we worried about earlier. The same delicacy that makes quantum coherence hard to maintain makes quantum systems exquisite detectors. What you should sit with is this. The strangeness of quantum mechanics is becoming a toolkit. We are not just trying to understand the weird rules, we are using them. The next decade will see quantum sensors deployed in medicine, geology, navigation, defense, and basic science. They will reveal things about the universe that no other instrument can see. Reality, it turns out, is harder to trust precisely because it is so rich. Every time we look more carefully, we find more there than we expected. In the next chapter, we examine the question of what all of this means for the most personal of beliefs: free will. You decide to raise your hand, your arm rises, you experience the choice, you experience the action. The two feel connected, but under your skin, billions of neurons fired, each driven by chemistry, each driven by physics, each driven by quantum mechanics. Where in that chain does your choice actually live? This is the free will problem, and quantum mechanics has reopened it in a way the classical world never did. In a purely classical universe, the answer is grim. Every neuron's behavior is determined by the laws of physics acting on the prior state of the brain. The prior state was determined by an earlier state, and so on back to the Big Bang. If you trace the chain far enough, the choice you just made was set in motion before you were born. The feeling of choosing is real. The choice itself, in the strict sense, is not. Classical determinism rules out free will, in this strong sense. Most people find this uncomfortable. Most philosophers have spent careers softening the blow, redefining free will as something compatible with determinism. A choice can still be free, they argue, if it follows from your own beliefs and desires, even if those were themselves determined. Quantum mechanics adds a twist. The universe is not, as far as we can tell, fully deterministic. Quantum events have genuinely random outcomes. The decay of a single atom is unpredictable. The result of a measurement is unpredictable. The classical picture with its iron chain of cause and effect is replaced by a probabilistic one. Causes lead to ranges of effects, weighted by probability. This sounds like good news for free will. If the universe is not strictly determined, maybe your choices are not strictly determined either. Maybe there is room in the gaps for something genuinely free. The problem is that randomness is not freedom either. If your choice to raise your hand was determined by a random quantum event in your brain, the choice is still not yours. It is the universe's coin flip. You are not the author. You are just the location. For free will to be real in the strongest sense, something more is needed. Some philosophers argue that what we need is a form of agency that is neither determined nor random, but somehow shaped by the agent itself. What that means, exactly, is hard to pin down. Most physicists find the idea suspicious. There is a stranger possibility. Some interpretations of quantum mechanics, like the relational or the many worlds view, treat the boundary between observer and observed as fluid. In those frameworks, the line between you and the rest of the universe is not sharp. The choices you make are not events that happen to you. They are events that constitute you. There is no separate self watching the brain operate. The brain operating is the self. Picture a river. The river is not separate from the water flowing through it. The river is the flowing. Asking whether the river chose to bend at a certain point is the wrong question. The bending is the river. In a similar way, asking whether you chose to raise your hand may be asking the wrong question. The raising is part of what you are. This does not give you classical free will. It changes the meaning of the question. Free will, in this view, is not about whether your choices were determined or random. It is about whether the process that produced them is identifiable as you. If it is, the choice is yours, in the only sense that matters. Whether this dissolves the problem or just renames it is a philosophical question. Different thinkers come down differently. What is clear is that quantum mechanics does not rescue the simple, classical idea of free will. It does, however, soften the iron determinism that older physics seem to require. There is room for ambiguity. There is room for genuine novelty in the universe. Whether that ambiguity is the seat of your freedom or just a mathematical curiosity is, ultimately, up to you to decide. The strange thing about that statement is that, in some real sense, the universe is deciding it through you. In the next chapter, we turn to one of the most contested ideas to come out of quantum cosmology: the possibility that our universe is one of many. The universe we live in is one bubble in a sea of bubbles. Each bubble has its own laws, its own constants, its own history. We happen to live in one where the rules permit galaxies, stars, and people. Most bubbles do not. Most are empty or unstable, or filled with conditions no chemistry could survive. This is the multiverse hypothesis. There are several versions of it. None are confirmed. All are taken seriously by mainstream cosmologists. The simplest version comes from quantum mechanics directly. The many worlds interpretation, which we met in an earlier chapter, says every quantum measurement spawns parallel branches of reality. The universe is a single branching wave function. We are one tree twig in an unimaginably vast forest. Everything quantum mechanically possible happens, somewhere. A second version comes from cosmology. The standard model of the early universe says, space underwent a period of rapid expansion called inflation, blowing up by an enormous factor in a tiny fraction of a second. This solved several puzzles about why the universe looks so smooth and so flat, but the details of inflation are tricky. In most versions, inflation does not end everywhere at once. It keeps going forever in some regions, ending only locally. Where it ends, a bubble universe forms. Where it continues, more inflation happens. The result is an infinite, expanding ocean of bubble universes, each its own cosmos. A third version comes from string theory. String theory predicts that the laws of physics depend on the geometry of hidden extra dimensions. There may be an enormous number of possible geometries, each giving a different set of physical constants. Combined with eternal inflation, this gives a landscape of bubble universes, each realizing a different geometry, each with its own physics. The number of possibilities has been estimated at around 10 to the 500th power. That is more universes than there are atoms in the universe we can see. Picture a vast pot of boiling soup. Every bubble that forms is a tiny universe. Most pop and vanish. A few persist long enough for things to happen inside them. Some, like ours, persist long enough for chemistry and life. The soup keeps boiling forever, producing new bubbles without end. This is, depending on your taste, the most beautiful idea in physics or the worst. It explains the apparent fine-tuning of our universe. The constants seem suspiciously good for life. Why? Because in a multiverse, almost every constant is realized somewhere. We exist in the universe where the constants permit us, because we could not exist anywhere else. This is called the anthropic principle. Critics argue that the multiverse is not science. It is not testable in the usual sense. You cannot visit another bubble universe. You cannot send a signal. The whole framework can feel like a way to avoid hard questions by waving them away with infinite possibilities. Defenders argue that the multiverse follows from theories we have independent reason to believe. Inflation explains the structure we see in our universe. String theory may unify the forces. If these theories are true, the multiverse comes along whether we like it or not. We should not throw away the predictions just because we find them aesthetically uncomfortable. There may be subtle ways to test multiverse hypotheses. Some scenarios predict tiny imprints on the cosmic microwave background, the faint glow left over from the Big Bang. If two bubble universes collided long ago, we might see a circular pattern in the radiation. So far, the searches have come up empty. The hunt continues. What you should take from this is humility. The universe we see may not be all there is. Reality may be far larger than the visible cosmos. Our position in it may be more random and more contingent than we usually imagine. We may live in one of countless bubbles with no special claim to importance. Or there may be only one universe and the multiverse is a beautiful mathematical fantasy. Both are live possibilities. In the next chapter, we explore the strange link between information and reality. The idea that the universe might be more like a computation than a thing. In 1990, the physicist John Wheeler proposed an idea so radical that it took decades to catch on. He called it from bit. The slogan was simple: every physical thing in the universe at its most fundamental level is built from yes or no questions. Reality is information. The atoms are derived. The bits come first. Wheeler's claims sounded like philosophy. In the years since, it has crept into mainstream physics. The first hint was the holographic principle, which we explored earlier. The amount of information you can pack into a region of space is bounded by the area of its surface, not its volume. Information, not matter or energy, is the fundamental currency. The universe accounts for itself in bits. The second hint came from quantum mechanics itself. A quantum state is not a thing in the usual sense. It is a list of probabilities for measurement outcomes. Probabilities are mathematical objects. They live in equations. They describe knowledge. When you write down the state of an electron, you are writing down information, not weight or color. The third hint came from black holes. The entropy of a black hole is exactly proportional to the area of its event horizon, divided by a unit called the Planck area. Each Planck area on the horizon counts for about 1 bit of information. A black hole the size of a coin would have more bits than every storage device humanity has ever built. The matter inside is gone. The information is on the surface. The universe takes information seriously enough to balance its budgets in bits. The fourth hint comes from quantum information theory, a field that has exploded since the 1990s. Quantum information has shown that many physical concepts can be rewritten in informational terms. Entropy, energy, even space-time itself, in some recent proposals, may emerge from patterns of quantum entanglement among more fundamental degrees of freedom. Picture a video game. The game world looks like a forest or a city, but underneath, the game is just bits in a computer's memory. The trees and buildings emerge from how those bits interact. The wind blowing through the trees is a calculation. The world is the calculation, dressed up in graphics. If Wheeler is right, the universe may be the same. The trees are bits. The wind is bit arithmetic. The graphics are what conscious systems generate when they process the underlying information. This is not the same as saying the universe is a simulation in someone's computer. That is a separate claim. Wheeler's idea is more abstract. It says that information is the substrate, regardless of whether anyone is running it. Reality computes itself. If true, this changes our deepest sense of what the universe is. Atoms become patterns. Particles become packets of bits. Space and time become large-scale features of how information is organized. Gravity becomes a kind of compression algorithm, with mass curving the network of information around it. There are working models. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that two entangled particles, no matter how far apart, are connected by a tiny wormhole. The wormhole is geometry. The entanglement is information. They are the same thing. This is wild, and the evidence is currently theoretical, but the math is consistent. The conjecture suggests that space is woven from quantum entanglement. Pull threads of entanglement, and you pull threads of space. If true, the things we see are not the fundamental things. Distance, duration, mass, even existence may be patterns made of something more abstract. Information processes the universe into being. The implications for the question of trust are heavy. If reality is information, then what we see is a representation, a user interface. The deep structure is invisible to us, except through equations. We cannot point to the bits. We can only watch their patterns play out. This does not mean reality is fake. The patterns are still real. The atoms still hold together. The sun still rises. But it does mean reality is stranger than the simple picture of stuff floating in space. The universe may be a great calculation. Knowing this changes nothing about your day. Knowing this changes everything about your understanding. In the next chapter, we look at how the strangeness scales up to the largest structures in the cosmos. Look up at the night sky. Galaxies cluster in webs and filaments. The largest structures span hundreds of millions of light years. Between them lie vast voids of nearly empty space. The pattern looks like cosmic geography. The shocking truth is that this entire arrangement traces back to quantum fluctuations in the first fraction of a second after the Big Bang. This is one of the most beautiful results in modern cosmology. The structure of the universe at the largest scales is a magnified imprint of quantum noise from when the universe was smaller than an atom. Here is the story. In the earliest moments after the Big Bang, the universe underwent inflation, the rapid expansion we discussed earlier. During inflation, every region of space, no matter how tiny, was filled with quantum fluctuations. Particles popping in and out, fields wiggling, the vacuum doing its restless thing. Normally, these fluctuations are too small to see. Inflation, by stretching space at an enormous rate, blew the fluctuations up to macroscopic size. The quantum noise became baked into the structure of the universe. When inflation ended, those frozen fluctuations were the slightly denser and slightly less dense regions of the early universe. Slightly denser regions had a bit more gravity. They pulled in matter faster than their neighbors. Over hundreds of millions of years, they grew into galaxies. Less dense regions emptied out, becoming voids. The cosmic web we see today is a fossil of the quantum world. This is not speculation. Maps of the cosmic microwave background, the faint glow left over from when the universe was about 380,000 years old, show tiny temperature variations across the sky. The variations are exactly the size predicted by the quantum fluctuation model. The pattern matches the math. The connection between the small and the large is one of the great triumphs of modern physics. Picture a perfectly smooth sheet of dough. Sprinkle some quantum dust on it, then stretch the dough by a factor of 1 billion. The dust particles, originally microscopic, are now landmarks. They define the geography. The galaxies in your night sky are the dust particles, grown to galactic size. This means the structure of the universe is, in a real sense, contingent. The exact pattern of galaxies depends on which quantum fluctuations happen to occur in the first instance of inflation. A different roll of the quantum dice would have given different galaxies in different places. Our specific cosmic web is one possibility out of unimaginably many. Other regions of the multiverse, if it exists, would have different webs. Even more striking is what this implies about origins. The matter in your body was once part of the cosmic web. The galaxy that became the Milky Way pulled in clouds of hydrogen. Those clouds collapsed into stars. The stars fused elements. The stars died and scattered their elements across space. New stars formed from the debris. One of those new stars was our sun. A small disk of gas around the sun condensed into planets. One of those planets is Earth. The carbon in your cells came from dying stars. The stars themselves grew in regions seeded by quantum fluctuations in the very first instance of time. You are literally a magnified piece of quantum noise. The same restless vacuum we discussed in earlier chapters is the source of your existence. The strange does not just affect you, it made you. This connection deepens the philosophical weight of quantum mechanics. The theory is not just about particles in laboratories, it is about why anything exists in the form it does. The randomness of the early universe is the reason the night sky looks the way it does. The reason the Earth is where it is. The reason you are here. If the universe is on a microscopic level deeply non-local, deeply uncertain, and deeply observer-dependent, then the universe at all scales inherits some of those features. The seeds of strangeness are in the soil. In the next chapter, we ask what this means for the future. What new technologies and discoveries lie on the horizon as we keep pulling on the threads of quantum reality? Walk into a hospital in 2050. A patient lies on a table. A device the size of a hat is placed over the head. In a few minutes, the doctors have a complete map of the brain's activity, neuron by neuron, in real time. There is no radiation, no needles, no expensive magnets. The device is a network of quantum sensors. The map is made of the brain's own magnetic whispers, read by atoms that listen. This is one of many possible futures unlocked by quantum technology. Some are nearer than you think. Some are still decades away. All of them rest on the strange physics of the previous chapters. The first wave is sensors. Quantum gravimeters, magnetometers, and clocks are already in advanced prototypes. Within 5 to 10 years, they will be in commercial use. Mining companies will deploy gravity sensors to detect ore deposits. Defense agencies will use them to find submarines. Medical clinics will use magnetometers to image hearts and brains with new clarity. Each application is built on the same principle. Quantum systems are exquisitely sensitive to their environment. Pair them with the right readout, and they become eyes that see what nothing else can see. The second wave is communications. Quantum key distribution is already used for some military and financial links. Over the next 2 decades, the technology will spread. National networks will link cities. International networks will link continents. By 2050, much of the world's sensitive data will travel through quantum-secured channels. Whether this stops cybercrime is another question. Whether it changes who can spy on whom is certain. The third wave is computing. Quantum computers are starting to perform specific calculations that beat the best classical machines. Right now, they are not yet useful for most practical problems. Within 10 to 20 years, that will change. Drug discovery, materials science, optimization problems in logistics and finance, cryptography, each of these fields will be transformed when fault-tolerant quantum machines come online. The first companies and countries to build them will gain enormous advantages. A more speculative wave is quantum simulation. By using one quantum system to simulate another, scientists can explore phenomena that would otherwise be impossible to study. Quantum simulators have already been used to model exotic phases of matter, the behavior of high-temperature superconductors, and the dynamics of black hole horizons. As these tools get better, they may unlock new branches of physics and chemistry. They may also help us understand consciousness, life, and the structure of space-time itself. There is also the long shot. Some researchers are exploring quantum batteries that could charge instantly using entanglement, quantum engines that could exceed classical efficiency limits, and quantum sensors so sensitive they could detect dark matter or gravitational waves from the Big Bang. None of these are guaranteed. All of them are being pursued. Picture a toolbox. Most of the tools inside have been useless for a century, sitting in a drawer marked "Weird Physics." Suddenly, in the last 20 years, we have learned how to pick them up and use them. Each tool, in skilled hands, does something a normal tool could never do. The toolbox is the quantum world. The hands learning to use it are the scientists and engineers of our time. What this means for ordinary life is that the strangeness we have been exploring is becoming infrastructure. Quantum effects, once locked behind laboratory doors, are entering offices and hospitals and homes. They will reshape the economy. They will reshape security. They will reshape medicine. They will reshape almost everything that depends on information, sensing, or computation. The pace is fast. 5 years ago, many of these technologies were 10 years away. Now, several are entering commercial deployment. The next decade will bring real change. What you should take from this is excitement and caution. The same physics that makes reality hard to trust is becoming the engine of the next industrial revolution. If you are alive in 2050, you will live in a world built on principles that, today, only specialists fully understand. Reality may be strange. The strange is also useful. In the next chapter, we step back from technology and look at what quantum mechanics has done to the field of philosophy. For 2,000 years, philosophers asked one question above all others: what is real? They answered it in many ways, with atoms, with ideas, with matter and form, with minds and bodies. Then, in the early 20th century, a small group of physicists threw a grenade into the conversation. They said the question, as classically posed, has no clean answer. The world is not the kind of thing we assumed it was. Quantum mechanics is a philosophy bomb. Its fallout is still being measured. Before quantum mechanics, the dominant view among scientifically minded thinkers was that the world consisted of definite objects with definite properties, located in definite places, evolving in definite ways. Our measurements revealed those properties. Our theories described them. The world existed independently of us. We were just observers, taking notes on a play already in progress. Quantum mechanics challenged every part of that picture. Properties are not definite until measured. Locations are smeared. Even identity is uncertain. The act of measurement participates in shaping the result. The world is not a play we watch. It is something more like a conversation we have. Philosophers have spent a century wrestling with this. Different schools have responded differently. Logical positivists at first welcomed quantum mechanics. They argued that physics had finally caught up with their view that we should only talk about what we can measure. Properties that cannot be measured do not exist in any meaningful sense. The new physics confirmed this. The unmeasured electron simply does not have a position. We should stop asking metaphysical questions and stick to predictions. Realists pushed back. They argued that quantum mechanics, if it is the final theory, leaves the world barely describable. The math works. The intuitions break. Something must give. Either the theory is incomplete, or we need a more imaginative metaphysics. Many realists, like Albert Einstein and David Bohm, looked for hidden variables that could restore a more familiar picture. Phenomenologists, drawing on philosophers like Edmund Husserl and Maurice Merleau-Ponty, found quantum mechanics oddly congenial. They had argued, on independent grounds, that the world is given to us only through experience, and that the strict separation between observer and observed is a philosophical mistake. Quantum mechanics seemed to confirm this. The line between subject and object is fluid. Reality, in some sense, is co-constituted by perception. Postmodern thinkers, often dismissed by physicists, sometimes overreached. They argued that quantum mechanics shows reality is a social construction. Most physicists groan at this. The math constrains us. The experiments give the same results across laboratories and cultures. There is something out there that does not care about our opinions. But there is a kernel of truth in the postmodern reading. The world we describe is shaped by the questions we ask. We do not have direct access to a universe of pure things. Contemporary philosophers of physics work on more technical problems. What exactly is a measurement? When does a wave function collapse? What is the relationship between quantum mechanics and special relativity? These are not philosophical games. They are real questions whose answers matter for how we understand the world. Perhaps the most important contribution of quantum mechanics to philosophy is humility. The world is stranger than our best intuitions can grasp. The categories we use, object, place, time, cause, are useful approximations, not deep truths. The deeper truths are mathematical. We can write them down. We can use them. We cannot always picture them. Picture an instrument so finely tuned that when you play it, the strings vibrate not just in the air around them, but in the air in the next room. You can hear something different depending on where you stand. There is no single correct way to listen. The music is the same. The listening positions multiply. Quantum mechanics says reality may be like this. The truth is one. The valid descriptions are many. This is not relativism in a flabby sense. Some descriptions are wrong. The math constrains. But within the space of mathematically consistent pictures, the room for legitimate variation is wider than older philosophers imagined. What you should take from this is permission. Permission to hold tightly to the math and loosely to the metaphors. Permission to be uncertain about deep metaphysics while still doing useful work. Permission to be amazed. In the next chapter, we look at what quantum strangeness implies for the most personal question of all. What does it mean for you? You are sitting somewhere right now. Your body is made of atoms. The atoms are made of particles. The particles obey quantum mechanics. Every breath, every heartbeat, every thought passing through your brain involves the strange physics we have been describing. You are not separate from this story. You are an instance of it. This is a hard idea to sit with. Most of us go through life assuming we are solid creatures in a solid world. We have boundaries, we have continuity, we have memories that link who we were yesterday to who we are today. None of this seems quantum. It seems normal, familiar, real. Yet at the deepest level, the boundary between you and the rest of the universe is permeable. Air molecules pass through your lungs. Water molecules pass through your kidneys. Atoms cycle through your body constantly. The atoms in your hand today may have been part of an ocean wave a few weeks ago. The atoms in your brain may have been part of a tree in a different country years ago. The body you call yours is a slow river of matter passing through a pattern. The pattern is you. The pattern is also made of quantum effects. Your enzymes use tunneling. Your photoreceptors use single photon detection. Your magnetic sense, if humans have one, uses the same radical pair chemistry as the robin. Your DNA replication relies on quantum behavior of the chemical bonds. The fact that you exist as a stable organism, rather than dissolving into chaos, is a quantum achievement of staggering complexity. Even your sense of being a single self has quantum flavors. Your memories are stored in patterns of neural connections that are themselves built and modified by quantum processes. Your perceptions arrive through cascades of electrochemical signals that depend, at the smallest scale, on the same physics as photon polarization. The continuity you feel between yesterday and today is woven from these threads. Picture a candle flame. The flame looks like an object. It has shape and color. You can describe it, but every atom in the flame is being constantly replaced. The wax burns and turns to gas. The gas heats and glows. New molecules feed in from below. Old ones disperse above. The flame is a pattern of activity, not a fixed thing. Yet the flame is real. The pattern persists. You and I are flames, in a slow burn that lasts decades. This perspective is not nihilistic. It does not say you are nothing. It says you are a process, not a substance. The process is real. The substance is misleading. There is comfort in this, if you let it land. The fears we carry about identity, about loss, about the persistence of the self, soften when we see ourselves as patterns. Patterns can change without ceasing to be themselves. Patterns can grow. Patterns can leave traces in other patterns, the way a wave leaves traces in the sand, the way a teacher leaves traces in a student, the way you leave traces in everyone you meet. There is also responsibility in this. If you are a process, you are participating in the universe's larger story. The atoms passing through you are part of the cosmic web. The choices you make, however quantum uncertain they may be at the smallest level, ripple outward through other processes. You are not a passenger. You are a piece of how the universe unfolds. The strangeness of quantum mechanics, then, is not foreign to you. It is your own foundation. Every time you wake up surprised to be conscious, every time you marvel at being alive, every time you notice the impossibility of feeling so solid and continuous while being made of insubstantial flickers, you are responding correctly to the truth. The world is strange. You are made of the strangeness. You are also, somehow, the part of the strangeness that is able to notice itself. In the next chapter, we step back and ask what this all means for science as a whole. A century after quantum mechanics was discovered, we still do not agree on what it means. The math works. The predictions match experiment. The applications are reshaping the world. But the question of what is really happening beneath the formalism remains open. This is not a failure of science. It is a feature of how deep our questions have become. Every field of science eventually reaches its frontier. In biology, the question of what life is. In neuroscience, the question of what consciousness is. In cosmology, the question of why anything exists. At each frontier, the precision of the math meets the limits of human concepts. We can describe what happens. We cannot always say why. Quantum mechanics teaches us a specific lesson. Reality may have features that no simple intuition can capture. The world may not be made of things in the everyday sense. It may not have a single, observer-independent description. It may not respect the boundaries between cause and effect, near and far, before and after, in the way we naturally assume. Our brains, evolved to navigate medium-sized objects at slow speeds, may simply not have the categories to picture what is really going on. This is not a defeat, it is a discovery. The discovery that our intuitions are tools that work in a limited range, and that beyond that range, We must rely on math and experiment rather than gut feeling. Picture a hand-cranked engine in a museum. It is a beautiful machine. It has gears and levers, and you can turn the crank to see it work. But the gears tell you nothing about how a modern jet engine functions. The principles are too different. To understand the jet, you have to learn new concepts, new diagrams, new vocabulary. The old intuitions about cranks and gears actively mislead. Quantum mechanics is the jet engine. Our classical intuitions are the cranks and gears. We can use the gears to describe rough features of the jet, but to really understand it, we need new tools. Most people will never need to fully understand it. The engine works without their understanding. But for those who want to know what is happening inside, the journey is long and humbling. The progress of science, in this view, is not a march toward a final theory that explains everything in familiar terms. It is a slow expansion of the conceptual toolkit. We invent new ideas. We test them. We discard the ones that fail. We keep the ones that work, even if they hurt our heads. Over generations, the toolkit grows. Our descendants, raised on quantum intuitions from childhood, may find the strangeness we struggle with to be ordinary. There is also a humbler reading. Maybe our brains have hard limits. Maybe some questions, like what really happens when a wave function collapses, do not have answers in any picture we can grasp. Maybe we are like dogs trying to understand calculus. We can use the math, the way a dog can use a leash, but the deep meaning is forever out of reach. Most scientists are agnostic about which reading is correct. They proceed with the work. They build the theories. They test the predictions. They wait to see what the next century reveals. What you should take from this is patience. The story is not finished. We are still in the middle of one of the greatest intellectual adventures in human history. The discovery of quantum mechanics is barely a century old. We are still learning what it means. Future generations may look back at our current debates the way we look back at medieval arguments about the nature of motion. Cute, important in their day, mostly resolved by deeper understanding. In the meantime, every door we have opened has led to another door. Every answer has unfolded into another question. The universe keeps showing us that it is richer than we feared and stranger than we hoped. In the final chapter, we look at what to do with all of this. How to live with a reality that is harder to trust and richer to inhabit than we ever knew. The world is not what your intuitions tell you. Solid objects are clouds of possibility. Particles are connected across distances by threads that ignore space. The past is less fixed than it feels. Two truthful observers can describe the same event in conflicting ways. Time itself may not be fundamental. Your own existence is a magnified piece of quantum noise from the first instance of the cosmos. And somehow, in the middle of all this, you are reading a script about it, with a brain made of the same strange physics it is trying to understand. The natural response is dizziness, or fear, or a kind of weary skepticism, where you decide it does not matter because it does not affect your morning coffee. There is a better response. Curiosity. Awe. A slow, settling appreciation for how much more interesting the universe is than the cartoon version we were given in school. For most of human history, people lived inside small stories about the world. The earth was the center. The stars were nearby. The body was a vessel for an immortal soul. The universe was created last week, on a Tuesday, by a deity whose preferences were well known. These stories were comforting. They placed humans at the center of a meaningful drama. Modern physics has dissolved most of those stories. The Earth is a small rock around an average star in an outer arm of an average galaxy among hundreds of billions of galaxies. The cosmos is 14 billion years old. The body is a temporary arrangement of recycled atoms, meaning, if there is any, is something we make rather than something we receive. This sounds like bad news. For some people it is. For others, it is freedom. The smaller, cozier stories have been replaced by a vast and strange truth. The truth turns out to be more interesting than the stories ever were. Quantum mechanics is the most recent chapter in this dissolution. It has taken the last comfortable certainties, the ideas that objects have definite properties, that observation is passive, that cause precedes effect, and made them shaky. What remains is a universe that is genuinely participatory. The act of observing matters. The choices we make affect the descriptions we can give. The world is not a finished thing we describe. It is an ongoing conversation we are part of. Picture a piece of music. The notes on the page are real, but the music does not exist on the page. It exists when someone plays it. The musicians, the listeners, the room, the moment, all participate in making the music what it is. Two performances of the same piece are never identical. Both are valid. Both are real. Quantum mechanics suggests reality may be like music. The score exists. The performance is co-created. This is not a license to believe anything you want. Some performances are out of tune. Some claims are false. The mathematics constrains us. Experiments anchor us. We cannot simply imagine ourselves into a world where atoms behave however we like. But within the constraints, the richness of valid descriptions is wider than older worldviews allowed. What should you do with this? A few things. Hold your certainties more lightly. The things you feel most sure about, the solidness of your body, the linearity of time, the separateness of yourself from the world, are useful approximations rather than ultimate truths. Reality is more permeable than it feels. This is a doorway, not a threat. Pay attention. The universe is constantly showing you strange things. A leaf catches the light in a way that depends on quantum effects in the chlorophyll. Your eye absorbs photons one at a time, registering them through reactions older than dinosaurs. The water in your glass is, at the deepest level, an ocean of vibrating fields. Everywhere you look, when you look carefully, the world is doing something miraculous. Stay humble. We have learned a lot. We do not understand most of it. The next century may overturn things we currently consider settled. The right response to a strange world is to keep asking, keep listening, keep being surprised, and finally, marvel. You are a process of unimaginable complexity, made of patterns that the universe spent 14 billion years assembling. Capable of understanding, however partially, the rules by which all of it works. That is, by any honest accounting, a wonder. The strangeness of the world does not diminish you. It makes you possible. Reality is harder to trust than we thought. It is also far richer than we imagined. Both things are true. Both things are part of the same single, breathtaking fact. You are here, briefly, inside the most interesting place anyone has ever known. Use the time well.